Okay, so we are going to begin our discussion of algorithms with discussing how we compare algorithms. So, starting off, a algorithm is simply a series of steps that solve a specific problem. So, each step is what we assume to be a simple or primitive. That is the smallest sort of bit an algorithm can be. So, remember when we discussed about languages and strings. A string is composed of little characters. That's the smallest aspect of a string. Same thing for an algorithm. An algorithm is composed as a series of steps. That's the smallest little thing that an algorithm can. That's the little smallest little thing that a algorithm it consists of. So each step can be implemented, executed manually, and an algorithm has a finite description, i.e. the same description for all instances of a problem. And a instance of a problem, as we discussed before, is simply a particular case, a particular series of inputs and the expected output. So the instance of, for instance, a problem that is sort, there is one instance that has the input 4, 3, 2, 1. And we know this has the output of 1, 2, 3, 4. Right? Same thing. This is one instance. Let's call this instance x. This is another instance of a problem. Let's call it x plus 1, which is sort. Let's make up a random 3, 2, 1, 4. And in this case, the output of this instance, expected output, is again 1, 2, 3, 4. Okay? And so what's important here is simply that a algorithm has the same description for every single instance that you of a problem. Okay? So you have a problem, you have one series of steps that you use to solve the problem regardless of the input, regardless of the instance. So you'll see this in when you first start programming. This is something very important because you devise an algorithm and then you realize, oh no, the algorithm works most of the time, but then there's one or two cases where it doesn't work. So does that mean that the algorithm is correct? Probably not. It's not an algorithm in that case, right? It's not an algorithm in that case because if you're manually selecting, oh, do something different for this instance of a problem, then it's not an algorithm in that case. What really an algorithm is that you use the same description for every single possibility of a problem instance. So you may, at the beginning of your algorithm, say, okay, for all arrays that end in 1, do one algorithm. For all arrays that end in 4, do another algorithm. That's valid. But you can't really say an algorithm is, you have an algorithm for sort that basically just reverses the strings in O of n time because it doesn't work for other instances of the problem. And we are going to allow our algorithms to have some sort of state or memory. And so, and since an algorithm is a series of steps, the thing that runs the algorithm is a computer. So the computer is simply the thing that implements the primitive instructions. And in the case of modern computers, what would those primitive instructions be? I mean, they would be the ISA, instruction set architecture. They would be MIPS. They would be IA32. They would just simply be those little codes, those little opcodes that do something that basically the CPU does something when given, right? So remember from your computer architecture courses, uh, um, instruction is simply a opcode, i.e., like add, store, whatever, and a series of inputs, right? And then you give those to the CPU and it performs a certain task. So the next step up is the algorithm. The algorithm consists of all those little CPU instructions. So having a model like this allows us to automatically implement an algorithm i.e., it allows us to implement a program. This is how computers work. This is how you could write any program using some programming language like C. It gets converted to a series of primitive steps, i.e., the MIPS instruction set architecture, and then the computer takes those series of steps and performs the algorithm on some instance of the problem. So um, the model of the computation that we want to use is an idealized, and I want to emphasize this because it's important, is an idealized mathematical construct that describes the primitive instructions and other details. So with this computer, we want to ideally have something, the ideal computer that implements those primitive steps in a consistent manner, right? And we want basically all the computer engineers and computer scientists across the world to agree on this particular model of computation, on this particular computer, to say that when I write a paper that says my algorithm is super fast and super awesome, we want to be able to compare it with other algorithms that other engineers have proposed. And we need, in order to do that, we need to have a consistent model of computation. And so the model of computation is, the model of computation that we'll use is the RAM model. The RAM model. So before we get too far into that, I want to specifically emphasize that a model of computation is different from an actual computer. Okay? A model of computation is simply the abstract wrapper around a physical object, right? And we do this because computers change. Computers change constantly. The computers that I grew up with as a teenager are very, very different than the computers that you're viewing me with right now. Okay? So we need this model of computation because it would suck that I propose an algorithm and in 20 years, basically my paper is worthless because, you know, the computer I evaluated my algorithm on, it no longer exists. Right? So in that case, we need a model of computation that will exist throughout time, and we need it to basically be close to the physical computer, but not limited by the physical constraints of modern computers either. So why is that? So what are those physical constraints of a computer? In a model of computation, for instance, when we compare algorithms, for instance, when we talk about quicksort or merge sort, as we will do later in this lecture, we assume that the time it takes to retrieve a piece of memory is constant, right? We assume that the time it takes to retrieve a memory X from location Y, or the memory at location Y, is some time unit. But the physical computer isn't that, right? The physical computer, I mean, the memory might be in the CPU cache, in which case it takes only a couple clock cycles to retrieve it. The memory might be in the DRAM, loaded up into DRAM, which in that case, I mean, it will take probably thousands or millions of clock cycles, who knows, to retrieve it. Or worse, the piece of memory could have not been accessed at all yet, and it could be in the hard drive, in which case the computer needs to execute a whole bunch of actions to get the memory in the hard drive onto the RAM, and then get the memory from the RAM into the CPU cache, into the many layers of the CPU cache, and finally you could operate on it, right? So that's why we can't really compare algorithms on specific machines, because it would just be a different comparison. For every person would just have a different machine, and it will be just bedlam. So what we're doing is we have this model of computation that is the standard model of computation. We've shown you already the Turing model of computation, which is literally a finite state machine accessing a memory. So that is what the RAM model of computation is. It's built upon that Turing machine. A little more advanced because the Turing machine, trying to program a Turing machine, trying to program basically ones and zeros on a single dimensional tape would is an effort, to put it lightly. We designed, or we use the RAM model to basically have the basic primitive steps that most modern computers have, but also not too complex so that comparing algorithms comparing algorithms with machines 20 years from now won't make sense. Hopefully my whole stream of thought, hopefully you're with me. So how do we design the standard RAM model? Informal definition. Let's design it informally first. So informally, what is the thing that what is an input to the RAM model? We say it's an integer. All right, this is a holdover from Turing machines, right? From Turing machines, we know that pretty much everything could be represented by a integer. Any alphabet could be represented by an integer, by integers. So that's what our RAM model will take. So even if our algorithm, let's say, takes in a string, right? The RAM model says that our algorithm that this string will automatically be converted to some series of integers, right? Which is how computers currently work, right? ASCII is exactly that, converting letters to integers. Okay, so we assume that all numbers fit in a word. Again, not necessarily true. I mean, it's practically true in the modern case with 64-bit machines, but 30 years ago, machines were 16-bit, and it's very easy to find a number that's larger than 2 to the 16, right? Could you, watching, I want to give a moment. Can you think of a number that's larger than 2 to the 16? Okay, so this would be, I want to say it's roughly 64,000-ish, right? So if you're working with large numbers, let's say you're working with financial data, you're working with Elon Musk's net worth. I mean, you would exceed the size of the word immediately in 16-bit machines. But there are ways to work around it. I mean, even back in the day, you know, there are ways to work around the word limitation. You could instead of one word, you could have Excel say every number consists of 2, 3, 4, 5 words, and pretty much get over that limitation, right? So without getting too far into the weeds, in the RAM model, we're going to say every number fits in a word. Okay, the word is not a physical thing in this case. It's not X bit. It's just a word. It's a collection of bits that represents a integer. And then we have and then we have to get to our steps. And namely, we say that every step, every operation takes constant time. Operation, constant time. And we say that memory access, random access, also takes constant time. Again, not necessarily true, definitely not true with modern computers, but we have to simplify things in order to make any sorts of logical comparisons, in order to have any sort of hope of comparing algorithms and figuring out what's best. We need to simplify, and in this case, we simply say arithmetic comparison operations, constant time, memory access, constant time. And we also say pointers and stuff and addresses are also storable in a word, which is almost always the case. I can't think of a computer that had an addressable memory that was larger than a word. But I know some of you guys are computational historians and will correct me on that. Okay, so next, now that we have the basic operations, we need a way to compare input sizes, right? An algorithm is a series of steps you do on a input, and of course you need to compare the particular input sizes. You need to see how well the algorithm works as the input quote unquote scales up, as the input size grows. So we say that the input size is n, and in this case, again, each number in the input is a word. So we don't count like number of bits. We don't say, if inputs have huge numbers, they take longer than for inputs that have small numbers. An added complexity that doesn't really mean much. We just say if an input has n words and numbers, then it is of size n. We say comparing two numbers takes constant time. Again, this follows from the arithmetic and comparator operations that we specified earlier. Random access to an array of elements, constant time. Addition of indices, constant time. Basic arithmetic operations, constant time. Reading and writing to and from memory takes constant time, right? All of this follows from what we defined earlier informally. And one thing that we typically do not allow is functions like bitwise functions, such as and or, XOR, shift, etc. We don't typically say floor functions or ceil functions take constant time, and we don't say and we don't limit the word size. Now, we don't say these operations take constant time because computers, not all instruction sets have instructions that perform these operations in one clock cycle. I think that's the best way I could explain it. I know modern computers have kind of merged instruction sets, so there's not a huge amount of variety, and I'm not sure if x64 has a floor or ceil function. I think it does have the bitwise operators, but historically speaking, not all functions had not all CPUs had these operations designed into the processor, into the ALU. And so because of that, we say that these operations don't take constant time. Almost every CPU had every CPU. I can't imagine a CPU that didn't have a add function, right? An add operand. I can't imagine any CPU that didn't have a load operand. They had to have. I can't imagine any CPU that had what are other basic operations? And yeah, I can't imagine any CPU that didn't have an and function programmed in the ALU. But this and was typically one digits, taking one digits, like this, comparing this digit with this digit. It was comparing Boolean values. I don't think that every CPU had the bitwise and. And if I'm wrong, please do correct me. Please do let me know. But I'm not sure about that. All right? Anyway, this is convention. These don't take constant time, but these do take constant time. Okay, so let's cut here and then on to the next part.